Okay, in this lesson we're going to take a look at a few measures and we're going to calculate the greatest possible error. Okay, GPE is the measure of 1/2 of its precision. So if you're looking at the measure, whatever the amount is, precision, if you remember, is the place value of the rightmost significant digit. So you're looking at that place value of that rightmost significant digit. In other words, the last digit. Okay, so let's just dive in and do a couple examples and then I'll talk about the significance of it. For the measure of 2 3600ths centimeter, the precision is to the hundredths place. We can see that there. And its greatest possible error is 5/1000ths of a centimeter. You're like, how did we get that? You're basically looking at half of the place value that is the precision. So in other words, 0.5 times 100th, being its precise to the 100th place, would give us 5/1000ths of a centimeter. I'll explain what this all means in just a bit. Right now I really want to focus in on how do you calculate it. For the measure 2 3/8 inch, now this is calibrated a little bit differently because we're looking at a ruler. We're looking at 3/8 inch rather than looking at decimal place. The precision is to the 1/8 of an inch, so you can see that the smallest calibration is the 1/8 of an inch, and the greatest possible error is 1/16. In other words, half of 1/8 of an inch. So you would basically take the precision, that calibration, smallest calibration, 1/8 times 1/2, and here you have it in fraction form, and it gives you 1/16. Okay, for a whole number like 3,400 miles, the precision is to the hundreds place. So the greatest possible error is half of that hundreds place. So 100 times 0.5 would give you 50. Now the significance of all of this. We've done one where we had a decimal, one where we had a fraction, and one where we had a whole number. We're going to do a couple more and then I'll dive in on explaining the significance of each one. So here we have 1 400ths of a centimeter, very much like the one at the beginning. This is precise to the hundredths place, so immediately find your precision and multiply by 1/2. So we have it's precise to the hundredths place, so I'm going to put 0.01 times 0.5, and that gives us a GPE of plus or minus 0.005 centimeters. Okay, so what that means is that our actual measure, I mean, chances are this isn't going to be exactly 1 400ths of a centimeter, but our measure, it's rounded to the hundredths place. Our actual measure could have been as much as 5/1000ths, or half the next place value below this, or half above it, and it would have rounded to 1 400ths. Okay, in this case, we've got 0 to the right of a significant digit, so that 0 is significant, which means this is rounded to the thousandths place. So you'd take 0.001 times 0.5, and this are going to be plus or minus 0.005 10,000ths of a centimeter. So our actual measure could have been one place value over as high as 5, or one place value under as 5 below that. It's not really making sense probably until we start looking at a whole number. So let's say I have 110,000 miles that I've put on my car. Is it exactly 110,000, like on the dot? Apparently all these zeros here, I've probably rounded to that. So we're looking at our precision here. This is precise to the 10,000ths place, this second one right here. So what I'm going to do is I'm going to take 10,000. I'm sorry, I'm going to take 10,000, and I'm going to multiply by 0.5, and I will end up with right at 5,000, plus or minus 5,000 miles. So in other words, my greatest possible error for this particular measure is plus or minus 5,000 miles. In other words, my actual measure could have been as high as, if I'd add 5,000 to this, I'd have 115,000, or it could be as low as, if I take 500 or 5,000 away from this, as low as 5,000. So the actual range is somewhere between 105,000 miles to 115,000 miles, and I got that by adding this 5,000 to and from it. So you can see that you have to look at that next place value to decide about rounding up and down. So you're kind of thinking about rounding, but working backwards. Okay, here you can see, we're dealing with a fraction, and our calibration is to 1/4 of a mile. So we're going to take 1/4 times 1/2, and I'm going to leave it in fraction form, so you can see that it is precise. Our greatest possible error is plus or minus 1/8. In other words, the actual measure could have been as low as 5/8 of a mile, or as high as 7/8 of a mile. Okay, when we have a foot here, 12 foot. So I'm looking at this, and the precision here is the nearest whole foot. So precision is 1 foot, and when I take that times 1/2, and I can put that in 0.5 or not, this is going to be plus or minus 1/2 a foot. In other words, the actual measure could have been 11.5 feet all the way up to 12.5 feet. And I got that by adding the plus or minus my greatest possible error. Here I have calibration of 1/2. So I would take that precision of 1/2, and I'm going to multiply by 1/2. I'll do this one in fraction form. So I could see that my precision is plus or minus 1/4. The actual measure could have been 1/4 all the way up to 3/4. The 1/2 isn't all that precise right there, but our next one, we have 1 2/10 of a meter. So this is precise. If I go back to my place value, that's precise to the 1/10 of a meter. If I multiply that by 0.5, I can see that this would be plus, sorry, I got the plus or minus on the wrong side of that decimal. Plus or minus 5/100ths of a meter. So the actual measure could have been 1.15, in other words, 1 1500ths of a meter, all the way up to 1 2500ths of a meter. I think when you see that in terms of interval, what could have rounded to that, that kind of helps you, I'm hoping that helps you see the significance of greatest possible error, one direction or the other, above or below. Okay, in that same vein, we're going to be looking at a range, but now we're going to be looking at tolerance. Tolerance is the acceptable amount a measurement can vary from a given size. I think the best example that I can give to you on this is in any kind of manufacturing industry, anything that's being manufactured and distributed or sold to the public or to anyone, the manufacturer needs to provide standards or tolerance measures. I think earlier we had done an example about 75 meters of wire on a spool, that it needed to be within a certain range. It kind of gave you an idea that the manufacturer has to meet a standard. If they're advertising 75 meters on their spool, they have to be within, I think we calculated 1.5 meters either above or below that. And so that's called tolerance. And so tolerance is an acceptable amount that a measure can vary from a given size. The tolerance interval is the difference between the upper and the lower limit. The tolerance range is the range between the lower and upper limits. So we're going to do a couple examples. I'll just talk through a couple examples, and then we'll do a couple ourselves. Here I've got a measure of 10 200 thousandths of a centimeter, plus or minus 1,000th of a centimeter. So let's say you're manufacturing something and you need to be within certain specs. This means that if we're having plus or minus, it's very much like our GPE, our greatest possible error, but it's generally something identified outside of place value. Means that the measure may be as large as I can add that, or as small as I can subtract that. So I get this range, or this tolerance interval, of 10 and 201 centimeters, thousandths of a centimeter, all the way up to 10 and 199 thousandths of a centimeter. And the tolerance range could be written like this. Tolerance range and interval, I don't really care so much about keeping them straight. Actually, the terminology is absolutely vice versa when you're talking about statistics, so you'd have to change gears when we get to that. I just really want you to recognize that you calculate by adding or subtracting whatever that tolerance is. Okay, here we have an example of inch, and this is in fraction calibration. 2 3/4 inch plus or minus 1/16 means that the measurement may be as large as 2 13/16. In other words, we added the 1/16 to 3/4, or as small as 2 11/16, where we took 1/16 away from 3/4, to find out our largest and our smallest measure that would meet that spec. The tolerance interval is 1/8 inch, and the tolerance range is from 2 11/16 inch to 2 13/16 inch. And you're like, well, where the heck did the 1/8 come from? Because if you look at your lowest interval of 2 11/16 and take it away from your largest interval, or your largest limit, which is 2 13/16, you would have 2/16 left over. 13 minus 11 is 2/16, and 2/16 is going to reduce to 1/8. Another way you can look at that is you have this tolerance both below your measure and above your measure, and so this would be your tolerance interval is going to be double whatever that is. We saw that same thing up here, that our tolerance interval was double whatever our tolerance was. So we'll kind of use that down here as well. Let's say that we've got to find the tolerance range for 1,500 kilometers plus or minus 175 kilometers. Trying to figure out an example. An example, let's say that we have a satellite that puts out a signal, and it guarantees that its signal will be plus or minus that 115 kilometers from the tower. So I'm sorry, I'm saying this wrong. The range of the signal is 1,500 kilometers, give or take 175 kilometers. So we want to find out what that range and what that interval is. So what we're going to do is we're going to take 1,500, and we're going to subtract the 175. I'm sorry, I need to line that up, don't I? We're going to subtract the 175, and we'll come up with 1,325. So in other words, 1,325 kilometers. That will be our lowest, our lower limit. And then we're going to take 1,500, and we're going to add 175 to find our upper limit of 1,675. So this would be the lower and the upper gives us our range. And if I took 1,675 minus the 1,325, I would come up with 350 kilometer interval. Now again, we could have done that a little probably a little easier if I would have just said, well, it's whatever my tolerance is, double, because I have above and below my measure. Okay, so I think it's pretty easy when you're dealing with whole numbers, not so bad when you're dealing with decimals. Fractions take a little more thought. Let's say that, let's say we have the battery casing for the camera that I am taking these videos with. Has a little slot to put my battery in to charge it, to recharge it. That space is about 1.5 inch, and let's just say the camera has a spec that they need to create that space plus or minus 132 of an inch. So we want to figure out what's the range of the width of that space for my battery, and what is that interval. So really what we're going to do is we're going to take 1.5 minus the 1/16, so 1.5 minus, 1/32. And we're, oh man, we have to deal with fractions again, but hopefully you remember that I can rewrite 1/2 with the denominator of 32 by saying 16. Well, 16 minus 1 is going to give me 15 30-seconds. So that would be my lower limit. If I took 1 and I'm going to rewrite it as 16 30-seconds, and I'm going to add 1 30-second, I would end up with 1 and 17 30-seconds. So this right here is going to be my tolerance range. So I'm going to write TR here. So you see that? And then we could actually just take the 1 30-seconds and multiply by 2 if you want. We'll just kind of take the shortcut here. That reduces diagonally, would be equal to 1/16 of an inch. So there's a tolerance range of 1/16 of an inch for my battery to slide in that little casing.